Welcome to the next edition of the HP Discover podcast series. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host and moderator for this ongoing discussion on IT innovation and how it's making an impact on people's lives. Our next big data case study discussion examines how the nonprofit New York Genome Center manages and analyzes up to 16 terabytes of data generated each day from its genome sequence appliances. And we'll learn how the drive to better diagnose diseases and develop more effective treatments is aided by swift, cost-efficient, and accessible big data analytics. To hear how they exploit the vast data outputs to then speedily correlate for time-sensitive reporting, please join me in welcoming our guest. We're here with Toby Bloom, Deputy Scientific Director for Informatics at the New York Genome Center in New York. Welcome, Toby.
Hi, thank you.
First, tell us a little bit about your organization. It seems like it's a fairly unique institution, large variety of backers, consortium members. Tell us about it.
New York Genome Center is about 2.5 or 3 years old at this point. It was formed as a collaboration initially among 12 of the large medical institutions in New York. So Cornell, Columbia, New York Presbyterian Hospital, Mount Sinai, NYU, Einstein Montefiore, Stony Brook University, and I'm sure I will miss somebody in there, forgive me. But all of the big hospitals in New York decided that it would be better to have one genome center than have to build 12 of them. So we were formed initially to be the center of genomics in New York.
And what does one do at a center of genomics?
We are a biomedical research facility that has a large capacity to sequence genomes and to use the resulting data output to analyze the genomes and find the causes of disease and hopefully treatments of disease and have a big impact on healthcare, on how medicine works now.
Great. Now, when it comes to doing this well, it sounds like you're generating an awesome amount of data. What sort of data is that, and where does it come from?
So we have a number of genome sequencing instruments that produce about 12 terabytes of raw data per day right now. That raw data is basically lots of strings of ACs, Ts, and Gs, DNA data, from genomes from patients who we're sequencing. Those can be patients who are sick and we are looking for specific treatment for. They can be patients in large research studies where we're trying to use and correlate a large number of genomes to find the similarities that show us what the cause is of the disease.
Yeah, so when we look at a typical big data environment, like in a corporation, it's often transactional information. It might be outputs from sensors or machines. How is this a different data problem when you're dealing with DNA sequences?
Some of it's the same problem, some of it's different. So we're bringing in lots of data. The raw data, I said, is probably about 12 terabytes a day right now. That could easily double in the next year. But then we analyze the data, and I probably store 3 to 4 times that much data in a day. So in a lot of environments, you start with the raw data, you analyze it, and you cook it down to your answers. In our environment, it just gets bigger and bigger for a long time before we get the answers and can make it smaller. So we're dealing with very large amounts of data. We are planning on taking in, and we do have one research project now that is taking in streaming data from devices. And we think over time we will likely be taking in data from things like cardiac monitors or glucose monitors, other kinds of wearable medical devices. Right now we're taking in data off apps on smartphones that are tracking movement for some of the patients in a rheumatoid arthritis study we're doing. We have to analyze a bunch of different kinds of data together. We'd like to bring in medical records, full medical records for those patients and integrate it with the genomic data. So we do have a wide variety of data that we have to integrate, and a lot of it is quite large.
When you were looking for the technological platforms and solutions to accommodate your specific needs, how did that pan out? What works, what doesn't work, and where are you in terms of putting in place the needed infrastructure?
So the data that comes off the machines is in large files. And a lot of the complex analysis we do initially on those large files. And I'm talking about files that are from 150 gigabytes to 500 gig or maybe a terabyte each. And we do a lot of machine learning analysis on those. We do a bunch of Bayesian statistical analysis. There's a large number of methods we use to try to extract the information from that raw data. When we have figured out what the variants and mutations in the DNA are that we think are correlated with the disease and that we're interested in looking at, we then want to load all of that into a database with all of the other data we have to make it easy for researchers to use in a number of different ways. We want to let them find more data like the data they have so that they can get statistical validation of their hypotheses. We want them to be able to find more patients for cohorts so they can sequence more and get enough data. We need to be able to ask questions about how likely it is if you have a given genomic variant you are to get a given disease, or if you have the disease, how likely it is that you have this variant. You can only do that if it's easy to find all of that data together in one place in an organized way. So we really need to load that data into a database and connect it to the medical records or the symptoms and disease information we have about the patients, connect DNA data with RNA data, with epigenetic data, with microbiome data. And we needed a database to do that. We looked at a number of different databases, but we had some very hard requirements to solve. We're looking for a database that can handle trillions of rows in a table without falling over, tens of trillions of rows without falling over. Okay, and to be able to answer queries fast across multiple tables with tens of trillions of rows. We need to be able to easily change and add new kinds of data to it because we're always finding new kinds of data we want to correlate. So there are things like that. We need to be able to load terabytes of data a day. But I think more than anything, I had a lot of conversations with statisticians about why they don't like databases, about why they keep asking me for all of the data in comma delimited files instead of databases. And the answer, when you boiled it down, was pretty simple. It's that when you have statisticians who are looking at data with huge numbers of attributes and huge numbers of patients, the kinds of statistical analysis they're doing means they want to look at some much smaller combinations of the attributes for all of the patients and see if they can find correlation. And then change that and look at different subsets. And that absolutely requires a column-oriented database. A row-oriented relational database will bring in the whole database to get you that data. And it takes forever and it's too slow for them. So we started from that. We must have looked at 4 or 5 different databases. And Vertica was the one that could handle the scale and handle the speed and was robust enough and reliable enough. And it's our platform now. And we're just at the point of loading in the first of the data. Well, not the first of the data. We're still loading in the first round of our data. We're still in the tens of billions of rows as opposed to trillions of rows, but we'll get there.
Now, you're also in the healthcare field, so there are considerations around privacy and governance and auditing and, of course, price sensitivity because you're a nonprofit. How did that factor into your decision, and is the use of off-the-shelf hardware a consideration, off-the-shelf storage, or are you looking at converged infrastructure? How did you manage some of those cost and regulatory issues?
Regulatory issues are enormous. There are regulations on clinical data that we have to deal with. There are regulations on research data that overlap but are not fully consistent with the regulations on clinical data. We do have to be very careful about who has access to which sets of data. And we have all of this data in one database, but that doesn't mean any one person can actually have access to all of that data. We want it in one place because over time, scientists integrate more and more data and get permission to integrate larger and larger data sets. And we need that. There are studies we're doing that are going to need over 100,000 patients in them to get statistical validity on their hypotheses. And so we want it all in one place. What we're doing right now is keeping all of the access control information about who can access which data sets as data in the database. And we basically append clauses to every query to filter down the data to the data that any particular user can use. And then we will tell them what the answers are for the data sets they have and how much data is there that they couldn't look at. And if they needed the information on how to go try to get access to that.
So you were able to manage some of those very stringent requirements around access control. How about that infrastructure cost equation?
Infrastructure cost is a real issue, but essentially what we're dealing with is if we're going to do the work we need to do and deal with the data we have to deal with, there are two options. We spend it on capital equipment or we spend it on operating costs to build it ourselves. In this case, not all cases, it seemed to make much more sense to take advantage of the equipment that was out there, the software that was out there, rather than trying to reproduce it and use our time and our personnel time on other things that we couldn't as easily get. A lot of work went into Vertica. We're not going to reproduce it very easily. The open source tools that are out there don't match it yet. They may eventually, but they don't.
Okay. When we think about the paybacks or determining return on investment in a business setting, there's a fairly simple, straightforward formula. But for you all, how do you know you've got this right? What is it when you see certain, what we might refer to in the business world as SLA, service level agreements, or key performance indicators? What are you looking for when you know that you've got it right and when you're getting the job done based on all these requirements and from all these different constituencies?
So there's a set of different things. The thing I'm looking for first is whether the scientists who we work with most closely, who will use this first, will be able to frame the questions they want to ask in terms of the interface and the infrastructure we've provided. Right? I want to know that we can answer the scientific questions that people have with the data we have, and that we've made it accessible in the right way, that we've integrated and connected and aggregated the data in the right ways so they can find what they're looking for. There's no easy metric for that. That's going to be a lot of beta testing. The second thing is, are we hitting the performance standards we want? Okay, how much data can I load, how fast? How much data can I retrieve from a query? Those statisticians who don't want to use relational databases, they still want to pull out all those columns, and they want to do their sophisticated analysis outside the database. I eventually may convince them that they can leave the data in the database and run their R scripts there. But right now they want to pull it out. I need to know that I can pull it out faster. Right, that they're not going to object, that this is organized so they can get their data.
Stepping back to the big picture of what we can accomplish in a health level payback, when you've got the data managed, when you've got the input and output at a speed that's acceptable, when you're able to manage all these different level studies, what sort of paybacks do we get in terms of people's health? How do we how do we know we're succeeding when it comes to disease treatment and understanding more about people and their health?
So I think that the place that this database is going to be the most useful, though not by any means the only way it will be used, is in our investigations of common and complex diseases and how we find the causes of them and how we can get from causes to treatments. So I'm talking about looking at diseases like Alzheimer's, asthma, diabetes, Parkinson's, ALS, which is not so common but certainly falls in the complex disease category, in the sense that these are diseases that are caused by some combinations of genomic variants, not by a single gene gone wrong. There are a lot of complex questions we need to ask in finding those. It takes a lot of patience, a lot of genomes to answer those questions. The payoff is if we can use this data to collect enough information about enough diseases that we can ask the questions that say, it looks like this genomic variant is correlated with this disease. Well, how many people in your database have this variant? And of those, how many actually have the disease? And of the ones who have the disease, how many have this variant? I need to ask both those questions. Because a lot of these variants confer risk, but they don't absolutely give you the disease. If I'm going to find the answers, I need to be able to ask those questions, and those are the things that are really hard to do with the raw data in files. If I can do it, think about the impact on all of us if we can find the molecular causes of Alzheimer's that could lead to treatments or prevention, right? And all of those other diseases.
Well, great. It's a very compelling and interesting big data use case, one of the best I've heard. So I'm afraid we'll have to leave it there. We've been examining how the New York Genome Center manages and analyzes vast data outputs to speedily correlate for time-sensitive reporting. And we've learned how the drive to better diagnose diseases and develop more effective treatments is aided by swift, cost-efficient, and accessible big data analytics infrastructure. So join me in thanking our guests. We've been here with Toby Bloom, Deputy Scientific Director for Informatics at the New York Genome Center. Thank you so much, Toby.
Thank you, and thanks for inviting me.
And thank you also to our audience for joining us for this Big Data Innovation Case Study discussion. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host for this ongoing series of HP-sponsored discussions. Thanks again for listening, and come back next time.